47 million steps. That is how long this tiny machine ran before it finally stopped. It has the brain the size of a peanut. Just 5 states, 10 lines of code. How does something so simple produce a number so enormous? And why did it take humanity 30 years to prove that this specific robot is the ultimate champion? To understand the monster, we have to rewind. A Turing machine is the simplest computer imaginable. It has 4 parts. 1. An infinite tape. 2. A head that reads and writes zeros and ones. 3. A state. Think of this as the machine's mood. And 4. The rules. Read, write, move, change state. It's a clockwork universe. There is no randomness. If you start the machine on a blank tape, it will do exactly the same thing every time. It only stops if it hits an undefined rule. That is the HALT. Let's see how it works. We start on state A in a blank tape. He looks at the table and sees he must place a 1, go to the right and change to state B. Now, in state B, he has to put a 1, move to the left and stay on state B. And so on and so on. The Busy Beaver game asks, with n states, what is the longest the machine can run and still eventually halt? Busy Beaver of 1 is trivial. If you don't halt immediately, you will loop forever. And by the way, we do count the halting step, so Busy Beaver of 1 is 1. Just halt. Halt as the only instruction. Busy Beaver of 2 is 6 steps, Busy Beaver of 3 21, and of 4 107. Then we hit 5, and the math breaks. To understand how we get from 107 to 47 millions, you have to look at what the machines are actually doing. They aren't just moving randomly, at least not the ones that take a lot of time to halt. They are inventing algorithms. To actually see these algorithms, computer scientists use something called space-time diagrams. The horizontal axis is space, the tape itself. The vertical axis is time, with each new row representing one tick or step of the machine. The colored pixel, that's the machine's head, reading and writing. And when you zoom out, you stop seeing random binary and start seeing behavior. With 2 or 3 states, machines mostly just panic. They write some ones, run back and forth, and die. But at 4 and 5 states, we see counters. The machine effectively teaches itself how to count. It writes a number, runs back to the start, increments it, and repeats. Then we have bouncers. These machines bounce back and forth between 2 walls of data, expanding the walls slightly each time. And finally, we have the chaos machines. They exhibit behavior that looks completely random, creating fractal triangles and complex structures. The Busy Beaver 5 champion isn't just running around. It is performing a complex calculation related to number theory, especially the Collatz conjecture dynamics. The champion for 5 states is 47,176,870. We actually found this machine in 1989, but for 35 years we couldn't prove it was the winner. The problem was the scale. In the universe of 5-state machines, there are over 88 million candidates. While most are simple, thousands of them run for billions, even trillions of steps. We knew they ran longer than our champion, but we didn't know if they would ever stop. To solve Busy Beaver 5, a team of mathematicians built deciders, automated filters designed to spot infinite loops. The easiest filter called cyclers. If a machine's entire universe, its state, its position, and the symbols on the tape, ever repeats exactly, it's stuck in a loop forever. Then there's the space trick. If a machine never leaves a specific section of the tape, it only has a finite number of possible configurations. It's like a deck of cards. Eventually, you'll run out of new ways to shuffle them. If the machine does more steps than possible configurations, it will never halt. These filters cleared millions of candidates, but they couldn't catch the holdouts. These were chaotic machines that didn't just loop, they grew, creating patterns that looked like they were actually calculating something. This is the space-time diagram for Skeleton 1. It takes 8 billion steps just to complete a single cycle. But notice it doesn't return to the exact same spot. It's a translated cycler. The pattern repeats, but it's shifted across the tape. Because the tape is infinite, it will just keep marching forever. Of course, now we know, but it's not easy to prove. For decades, there were skeptics like Skelet 1 or Skelet 17. If even one of those eventually halted, the Busy Beaver number for 5 states would be trillions of times larger than we thought. To be 100% sure, the team used the COQ formal proof assistant. This is a specialized tool used to translate mathematical logic into code that a computer can check. It ensured that every step of their proof was airtight and that not a single human error was made during the sorting process. And in July of 2024, the last skeptic fell. The computer-verified proof confirmed it. Busy Beaver 5 is officially 47,176,870. You may ask, why don't we just write a computer program to calculate Busy Beaver of 6? Supercomputers are fast. We can't. It's literally impossible. In 1962, Tibor Radó proved that the Busy Beaver function is uncomputable. It grows faster than any function that can be calculated by a computer. It grows faster than the Ackermann function, faster than Graham's number, faster than 3 of n. If you could write a program to calculate Busy Beaver of n, you would solve the halting problem, which Alan Turing proved it impossible. Think about it like this. Busy Beaver of n is the maximum number of steps an n-state program can possibly take before it stops. If you knew the exact magic number, you could take any n-state program, hit run, and just count the steps. If the program crosses that Busy Beaver of n and still hasn't stopped, it never will. You would know with absolute certainty that it's trapped in an infinite loop. You would have built a perfect infinite loop detector. But Turing already proved that such a detector is a logical paradox. It cannot exist in our universe. Therefore, there is no algorithm to find the answer. We have to hunt these numbers manually, one by one, in the dark. And this is where it gets scary. It turns out you can encode famous open math problems into these tiny machines. Take the Collatz conjecture. Every even integer greater than 2 is the sum of 2 primes. We think it's true, but we haven't proven it. You can build a Turing machine that checks every even number. If it finds one that doesn't work, it halts. If the conjecture is true, it runs forever. Mathematicians have built this particular one with 27 states. That means if we knew the value of Busy Beaver 27, we wouldn't just have a number, we would know if Collatz is true or false. Though, of course, even if we started the machine today, no human would be there to see it cross the Busy Beaver 27 crossline, given how enormous this number is. Researchers have built machines where, if they halt, the Riemann hypothesis is false. Or if they halt, our standard axioms of set theory are inconsistent. These numbers contain the answers to the deepest questions in math. So what about Busy Beaver of 6? It is estimated to be larger than 10 to the power of 10 15 times. A stack of paper with this number written on it wouldn't just fit in the universe. The universe is too small to hold the digits. We have conquered 5. It took 30 years. But 6? We will likely never know the answer. And yet, mathematicians couldn't resist pushing the boundaries further. The classic Busy Beaver operates by very strict rules. A one-dimensional tape and only 2 symbols to write with. But what happens if we change the game? What if we give the machine 3 symbols instead of 2, or 4? Or instead of counting the time a machine takes to halt, what if we measure the space? How many distinct squares of the infinite tape can a 5-state machine put to 1 before it finally powers down? Theorists have imagined machines wandering across 2-dimensional grids instead of a flat tape. They have even explored what happens when you drop 2 different machines onto the exact same tape, leaving them to interact, collide, and override each other's code. The Busy Beaver reminds us that complexity arises from simplicity, and that some truths might be forever out of reach. And as always, thanks for watching.